and it is 10:35 on the dot. I think being a stickler for time is interesting. So today we'll be talking about demystifying quantum computing. And we need to discuss why this topic matters. I think we've heard about quantum computing in the same way we heard about quantum physics. That's the first time we had quantum anything, at least for me. But now we introduce bits or qubits or things like that. And we look at we look at the differences between what traditional computing is, what supercomputing might have achieved for us, and now quantum computing. And this session is meant to be insightful, help us understand for the people like us who do not quite understand what the implications of this are, get to understand that, and also learn about our space in this. Are we playing catch up? Are we ahead of the game? Should we be working towards it? But before we go into that, I'd like to have some housekeeping rules. First is to inform you that this session is recorded, and we will be sharing the recording with anyone who sorry. This session is recorded. We'll be sharing the recording with the people who would like to get the recording just to revisit it if they'd like to do it. The session is an hour. We'll have 35 minutes or around there of presentation and 10 minutes of active or live Q&A in the chat session. Please feel free to communicate or to ask your questions. Keep them as simple as possible. Try not to use a large language model to articulate it. Ask it from the honesty of what you would like to find out. And with that, I think we can kick off. First, I'd like to introduce Dr. Betsy and to invite her to give a small description from the iLab side. Sorry, I forgot. My name is Lynette Wanjira, and I'm from the iLab Department of Strathmore University, which is what you'll be told more about by Dr. Betsy. Karibu, Dr. Betsy.
Thank you, Lynette. Welcome, everyone, to Demystifying Quantum Computing webinar. I'm Betsy Murithi. I'm a research fellow at iLab Africa, Strathmore University. iLab Africa is a research and innovation center with a focus on ICT for development. The webinar is part of a series leading up to the Global Data Science Summit 2026. I'll put the link on the chat for anyone who's interested to find more about it and register. So leading up to the summit, we've been talking about different topics around harnessing AI and data ecosystems to drive public and private sector innovation. We also have a podcast, the Data AI Need, that's also dives deep on different topics. So today we've had a lot about quantum computing. So without further ado, should I pass it to Carrington or Shannon to introduce Quantum KE? Shannon, you can introduce Quantum KE. Your aim around quantum for Kenya, and then we can dive into the presentation.
All right. Thank you, Dr. Betsy, for the opportunity, and it's nice for us to have this webinar and I think to demystify quantum computing to everyone. I don't know if I'm in position to. Okay, let me just share my screen briefly to share about what Quantum KE is all about and our work within the quantum space. Okay. So this is a brief overview about our community and our work. So basically, Quantum KE, who we are a community of around 300 members. So we basically from students all the way to professionals to people who are in the industry, mostly within the tech ecosystem, engineers. So that's what our community comprises of. And we are people who are passionate about quantum computing and quantum information science in general. So we hold a number of focus areas include community outreach, education, research, and also projects. We also focus on projects as well. So under our education and talent initiative, so I'll just run through a number of things that we've been able to do and what's happening within our community. So because quantum is relatively a new topic to many, and the first thing is obviously capacity building, getting people aware, about what the community, what the technology is about, and how they can be able to apply it in their lives, and if they want to get started. So just unpacking the how and what of quantum computing and quantum information science. So we are, on that note, we are developing an academy as of now. So an online e-learning platform known as Quantum KE Academy. So it just basically aims to give people, the general public, beginner, anyone who doesn't have any background in quantum computing, on their hands-on of what is quantum, the different applications, use cases, and so on and so forth. So that's one of our flagship projects that is currently underway. We are currently in phase one, where we've completed the first module for the beginner 101 pathway. Then the other thing, we also have a member of our community. He's known as Brian. For him, he's also a master student at the University of Oxford. He's developed an application where you can be able to go and learn about quantum. So this is also live. So it's more of a community engaging, e-learning platform. You're able to kind of play around with the quantum circuits because it also has an integrated platform on the site. So it's also worth checking out for those of you who are curious and would like to know more about quantum and how just to play around with the circuits and how it works, on the programming side especially. Then the other thing is on Q Kenya Hub. So we recently partnered with QWorld. QWorld is an organization, it's a global organization that has different member countries, and Kenya being the recent one which was added. We are part of what is called now a QCASI network, which is like a group of different countries collaborating together to ensure that we promote quantum science and technologies across our different regions. So QWorld is basically an education platform, and they offer like different course levels, right? Different course levels. So we just got recently established 2026. So we offer different courses that are certified by QWorld, since they already have the expertise and the trainers. Yeah. So for under Q Kenya, we were able to organize our first QBronze workshop. So QBronze is basically like the introductory diploma workshop on the basics of quantum computing. So these are some of the topics that are covered, including the difference between classical systems and the quantum programming, then the different types of operators, qubits, and then the states, and so on and so forth, right? So, and then at the end of the course, of course, we had a number of people who completed the course, and they're given a certified diploma certificate from our end and also from QWorld. Beyond that, we also have the Qiskit Fall Fest. So this is in partnership with IBM. So in 2025, we hosted the first Qiskit Fall Fest in partnership with Strathmore University, the Institute School of Engineering, and computing. So for this, we had about 30 participants or so, and they were able to learn through the basics of Qiskit. So basically, Qiskit is like the quantum computing side of IBM. So they were able to learn some programming basics, and then after the whole program, they were also given a certificate, and they were able to show competence in using Qiskit, programming different circuits, and so on and so forth. And then we also have pioneering work in research. So some of our members, so we have our lead who's actually at the currently in Poland, and he's doing his master's in liquid crystals. So this is in material science. And we have a number, there's also one who's also doing simulation of drug discovery in leukemia. So basically using quantum machine learning. I think Dr. Bitsy has spoken about the data science. So this is how quantum can be both intersected with different disciplines, such as AI and machine learning. So basically leveraging quantum algorithms to speed up the process of drug discovery in cancer and leukemia. In terms of community, what we do around community, so we have meetup events. As you can see in the pictorials, we have what we call Entanglement Saturdays, where we meet monthly and then we go through different topics from quantum error correction to different use cases, different applications in industry, with our previous one being quantum applications in finance. So that was our previous Entanglement Saturday, and we'll be having one upcoming one this coming Saturday actually, and the discussion will be around quantum networks. So in terms of how we work, we also have webinars and boot camps. Here you can see we have different webinar series. We also have X Spaces, where we tackle more softer topics in terms of applications, careers, opportunities. And then, we also try to make it fun. We have happy hour, trivia night, karaoke in partnership with Blockchain Center. And we try to make quantum and learning fun as well. Last year, we had the International Year of Quantum, where we were marking 100 years of quantum mechanics. So different ecosystem partners were celebrating through workshop events, summits, and so on. And on our end, we were able to organize the Africa Quantum Summit last year around December, and it was a successful event. You can find out more by visiting the africaquantumsummit.com, see the areas that we discussed around talent development, academia, research, partnerships, and so on and so forth. We got a lot of traction and interest from ecosystem partners, and they're seeing the need of learning, and of learning what quantum is all about and how we can be able to position Kenya and Africa as a whole in the race of quantum supremacy. So these are various partners we've worked with before. We still have more as time goes by. Yes, so that is a summary of what you do as Quantum KE. And we look forward, if anyone wants to join our community, feel free to join through our website, quantumke.org, where you'll find you'll be involved in most of our in our different activities, such as the workshops, webinars, and other education initiatives. Yes, so thank you so much. Now I'd like to invite Carrington to take us through the Quantum 101 session. I know that is what many people are looking forward to. So Carrington, Karibu, I think now we've given them a good background. So over to you.
Thank you, Shannon. I will share my screen. Okay, can you see my screen? Yes. If you can see my screen, thank you.
Yes, you can.
First, yes. My name is Carrington Kinyanjui. I am affiliated with multiple organizations. One is Songhai. Songhai is a fundamental AI research company in Kenya. So this is a research-oriented company that I work as the CTO. But I am also a researcher of a sister company called Haki Artificial Intelligence Africa. For those of you who have used Haki, the legal assistant tool, we are the team that developed that tool. And we are looking into developing multiple other AI tools this year and next. I am also a PhD student at the University of Manchester, where I'm studying the application of natural language processing, so the field of computer science that delivered ChatGPT, Gemini, etc. In historical scientific networks. I am also a teacher, a lecturer at the Open University of Kenya, where I am also at the AI and data science department, basically teaching deployment in machine learning. I will start teaching in a few months. So any of you who are interested in joining up in this course, please let me know. I'm not going to talk about these things. I am going to talk about quantum computing, which is part of the work that I do at Songhai, especially quantum machine learning. I am going to introduce the concepts, the basic concepts, and then we are going to look at basically what is quantum mechanics, okay? We are going to look at what is quantum computing, what is computing, sorry. And then we are going to start thinking about how to synthesize quantum mechanics and computing, okay? And this is what will give us this story of quantum computing. And then after that, we will start thinking about ways in which Kenya can benefit from the technology and through inaction, the risks that this technology poses to Kenya, for example, okay? So it will be three-phase approach. It will be a three-phase approach. And I hope that these concepts are built as we move along. So thank you very much, Strathmore, for having me. And thank you very much, Quantum Kenya. I will move on to the next slide. So why do we need quantum computers, okay? I would like to pose to you that computing is a physical process, okay? Typically, when we think about computing, we think about opening our laptops, pressing buttons, and then stuff comes up in the screen. We read the information, and we therefore interact with computers with all of the physics locked behind a box. And because of that, we use this physics locked behind a box to start asking silly questions in the internet. For example, where is this physics going to take me? Because someone has abstracted, someone has hidden the physics, someone has hidden the engineering behind a box, you are able to ask such questions in the internet. And that's someone who has hidden the physics and the engineering and the science behind the box makes $1 billion out of your ignorance. So the first point I would like to pose to us is that there is a physical process, that is a process governed by the laws of physics that governs computation. And it is something that it will be the basis of everything we are going to discuss. Computers, as they are currently construed, are called classical computers, okay? Computers largely work on the basis of classical physics, although this is not generally true. Even your laptop has some aspects of quantum mechanics that help it process information faster, okay? And that's why we have these things called semiconductors, conductors that conduct some of the time because of quantum mechanics and atomic physics, okay? So it is important to consider that these systems are largely classical. When we are speaking about ones or zeros, and I will introduce this concept in the coming slides, we are talking about, we are sure that the system of your computer is in this state, or it is in this state. And then it can go from this state to that state by the process of computation, okay? So again, computation is a physical process, and the physical process that governs your current laptop is a classical physical process, okay? Now, quantum computers will come in where there are some problems that your computer, your current laptop, even when scaled out 10,000, 15,000 times, cannot solve such problems. Now, quantum computers expand the kind of problems that we can solve and the kinds of ideas that we have access to. And this is why we need to understand quantum computing. But remember, it is not in general. A quantum computer is not a box of magic. It is not a magic wand, okay? You don't wave it at problems and problems reorganize themselves according to your wand. No. Quantum computers are specific physical objects that can do specific physical things better than the physical object that is currently your computer. And we will also explore the applications for this in science and security. And I would like to show you some of this. Now, I was asked never to show equations when presenting in another place other than classes. But you see, I am a product of Kenya's education system, so we don't follow instructions very closely. So forgive me as I show you this one equation, just this one, and then we will continue. Take it as the necessary drug that you need to take. Take it as your mboga, as your kales that you need to eat so that you can get your meat. This equation is called the Schrödinger equation, okay? Developed by Erwin Schrödinger, an Austrian physicist in the 1920s. It expresses the total energy in a system. So if you see that H with a thing on top of it, that actually is kinetic energy plus potential energy. And for those of you who stuck with physics throughout the 4 years, you know kinetic energy, the energy of motion, plus potential energy, the energy of position in a space, right? For example, when you are up in a hill, that is very high energy. You know that the combinations of these give the total energy of a system. And physics is the study of energy and its relation to matter. That's all it is doing. So this equation relates the energy of a quantum system to the matter of a quantum system. I would like you to focus on this thing that looks like a fork or a sort of trident, Poseidon's trident, for example. That thing is called the wave function. It is called the wave function, and it is as important for quantum computing as semiconductors are for classical computing, okay? That thing is called the wave function. So this is my first piece of jargon, and you should note it down. Now, it has come to be understood over a period of 100 years. So even physicists themselves have taken a lot of time and they still don't understand this process properly. But it has come to be understood that this thing in quantum mechanics, and quantum mechanics is the study of very, very small objects, atoms, molecules, particles, things like that. This object, this fork in quantum mechanics represents everything that we can understand about a system, a quantum system, okay? Even you have a wave function, it's just that it is infinitely complicated. It is very difficult to understand you using your wave function, so it's just easier to talk to you. However, for quantum systems, we can ask this wave function certain questions and it can then answer us if we are very, very careful with the kind of questions we ask. You have heard Shannon talk about operators, okay? So an operator is the thing, the tool that we use to ask these questions. And for example, that H there is an operator, okay? An operator is a question, how you ask questions in atomic physics. One final piece of jargon. Actually, I am done. What we do is look at this wave, okay? Look at its amplitude, so the crest and the trough, okay? And we use this manipulation of the wave, and that's why it's called a wave function, to answer questions about physical systems. And that is quantum mechanics for you, basically. You take this wave, you study how it is flowing in time, and then you measure it at a particular moment, okay? And this goes as the wave is squared, okay? So to get your answers, you need to sort of square the wave. Now, quantum mechanics, because it relies on the structures of waves and not particles, has a lot of strange properties that are interesting for us and are going to be interesting for us when we are talking about quantum computing. So the first one is called superposition, okay? Superposition. This is my jargon slide and then I am done, I promise. Just like this was my equation slide, this is my jargon slide. So pay attention and then the rest of the stuff I'm talking about will be very easy. One is superposition. Superposition is this idea that a wave can have multiple states that individually are in opposition to each other, but they can both be the consistent properties of a wave. So a wave, for example, can be simultaneously up and down, okay? As long as it is in different parts of the wave. It can be moving like this and moving like this in opposite directions, moving to my right and moving to my left. And this idea that waves can encode multiple properties that are opposite instantaneously is important for our consideration. Yes, Rogers, quick question.
I'm just wondering whether you are, it was the slide, because we're on the previous slide, so I was just wondering whether you are still on the same slide.
Yes, I was using that slide to explain this slide. Yeah, thank you. A second property is interference. When waves meet each other, okay, and they have opposite properties. So at a particular position, so this is the picture in the second picture in this slide. So the wave with dotted lines is going down. The wave with red lines is going up. So when these meet, they will cancel each other out and you will end up with a straight line, the thing there in the middle. This is called a destructive interference. It has destroyed the waves. And when it does the opposite, where two peaks are meeting together like that, they will add up and create a bigger wave. This is called constructive interference, okay? Destructive, constructive, destructive, constructive. There's a third property that is very interesting for us called entanglement. Again, you can understand it using waves. There's a certain part of the wave, when it's up, the other part is down, and when it's down, the other part is up, okay? So it does something like that, Sindio. That is how you understand that you are in wave motion. That thing for quantum mechanics is called entanglement. That the properties of particles, atoms, molecules described by quantum mechanics exhibit this property. They behave like waves. So they're able to have properties that are entangled. Entangled means that my properties, just like the usual entanglement, when you're entangled with your partner, some of your properties depend on your partner and some of your partner's properties depend on you. Something very, very similar, okay? Not very similar. I mean, we are not quantum systems per se, but that is how you should understand this system. And this entanglement can be destroyed or created, okay? Fourth thing we need to think about, measurement. Typically, when you are in a physics lab or when you're in a biology lab, all you need to do to measure is have a ruler or something like that, or a voltimeter or something like that. And you just record the value and you're done, okay? The problem with quantum mechanics is that measurement is a very interesting part of the physical process, okay? When you're reading, for example, when I'm reading this laptop, I am measuring brightness features on my screen. That is what I'm doing. That is what reading boils down to of your mobile phone or your laptop. But measuring in quantum computing is very interesting. Because this wave is moving around, when you make a measurement, at least one interpretation of quantum mechanics says you destroy this wave. And what happens is that an answer snaps. So if it was both up and down, okay? When you make a measurement, it is either up or down. And this destroys these earlier features that we have spoken about. Superposition is destroyed by measurement. Interference can be destroyed by measurement. Entanglement can be destroyed by measurement. And you must start thinking about, when you're an engineer, how do you mitigate for these factors when you're not ready to measure? Okay, so you have to close the box. In quantum computing, you have to find ways of closing the box. The last feature is uncertainty. Okay, we cannot be sure, just like if I ask you, where is that wave? Well, you can say this wave is between 5 meters and 10 meters. You cannot say this wave is at 0.0001 centimeter. No. A wave is described by ranges, and similarly, the particles that are governed by quantum mechanics are described by ranges. And this is an extremely important feature of the field. So we've done quantum mechanics, just 2 slides. I wanted you to suffer for 2 slides and then I leave you alone. One, what is the primary constructions of quantum mechanics? What are the bricks we use to build quantum mechanics? And what are the features of this house we have built that are interesting for us in computing? For reference, each of these slides is at least a course at university. So I have definitely not explored them in full. Now, let us talk about computing. I have earlier tried to sell you this idea that computing is a physical process. It is a process governed by physical laws. And if we take time and understand the physical laws that govern this process, we can then build computers, new computers on the basis of the physical processes that we have understood, okay? And biology is another physical process. And therefore, you can build computers on the basis of biology, and this is the basis of biological computing. And it is hypothesized that one good example of a biological computer is you, okay? So this is the idea. Computing is an extremely general feature of the universe, okay? At its very basic, computing is the controlled transformation of information. Okay, for those of you who have taken computer science and engineering classes, this is obvious. This is a good compression of the process of computing, okay? And typically, when somebody is introduced to computing, you focus on 3 things, okay? Mambo matatu. 1, input, okay? So we have certain pieces of information encoded as physical states entering the system. This is called input. You have taken your finger, pressed on P in your laptop, okay? That is an input. Pressed on J, pressed on O, pressed on Y, that is an input. After that input is taken by the system, something needs to be done to it, okay? Some physical processes which have informational results need to be done on it. This is what you call processing. And then it will go to, in the case of our laptop, it's just voltage, okay? It's current moving around in the processor, in your semiconductors, in your Core i7s, Core i9s, in your GPUs. Next thing, it will go to some part where I, the user, can see what is happening inside the computer, okay? So that is called the output, okay? So input, process, output. And all forms of computation, no matter how complicated they are, depend on these 3 things: input, process, output, input, process, output. So whenever you're meeting a nasty problem in computation, yes, even artificial intelligence, just focus on what is the input, what is the process, what is the output. And basically you can decode the computational process. But there is another part of the architecture that people don't typically talk about, but is very important. And this architecture is called memory, okay? So you need to be able to store intermediate states in a physical device so that you're able to carry out computation. When I press J on my laptop, okay, it needs to be stored somewhere before it gets to the screen. So there's need for memory in the input. There's need for memory in the processing because my computer's brain cannot hold all information at the same time. There's need for memory when I'm putting output because I cannot show everything at the same time. So memory is also an important factor. And that is how you achieve, that is how you implement logical operations in a physical process. And that is another definition of computation, the representation or implementation of logical processes in physical objects. Now, how do we do this in our computers? I have spoken about classical computers. How do we achieve this classically? How does your laptop work? Your laptop, because of very, very clever engineers in the 30s, 40s, and 50s, mostly in the 40s and 50s, just after the war, the World War, figured out the Second World War, for the historians here, figured out that you could essentially build arbitrary types of information out of only two things, a 0 and a 1, a down and an up. And by combining down and up in various sequences, you can essentially represent any arbitrary piece of information. And because you can combine just two types of bricks and build the house and arrange it in whatever manner you want, build a mansion, build a bungalow, build a bedsitter, it became clear that 0 and 1 could be used for something called universal computation. Universal computation, just like the Universal Church, the Catholic Church, is meant to show that it can do any arbitrary form of computation. So do I want to press J in my laptop? That is a form of computation. Do I want to watch my latest series? That is a form of computation. Do I want to watch Argentina losing the World Cup? That is a form of computation. All these are forms of computation and can be constructed by zeros and ones. And how do you do that? Using things called logic gates. Logic gates are, go back one slide, the controlled transformation of information. So how do we control, transform our information in a controlled way? By using these things called logic gates, okay? So if a logic gate that is on the right side, on my right side of the slide, that picture, if it gets a 0, it will transform it into a 1, okay? If it gets a 1, it will say not 1. What is not 1? The other brick 0, okay? And if it gets both 0 and 1, it is only allowed to show 1 without if both the inputs are 1. So 0 and 1 will give you 0 because both inputs need to be 1 for it to fire, for it to show, okay? And then 0 or 1 will show 1 in case there's at least just one on bit, okay? So I want you to understand, if you haven't muted, please mute. If you haven't muted, please mute, thank you. So I would like you to understand that we can transform input bits into output bits. 0 and 1 can be transformed various ways into output bits, okay? And this is important. And your laptop works on the basis of this very simple operation. You take a lot of this stuff and chain them together, you end up with the mansion that is your laptop. And whenever you hear digital, we are going digital, What we are trying to say is that we are encoding our information in such a way that it is manipulable by these gates. Okay, your laptop works on the basis of logic. Now, your laptop is clearly powerful. It is clearly helpful. Yes, Lynette?
I hate to be the one to bring this news, but you have 10 minutes. I wish I would give you forever. Yeah.
The problem is that
But-
I also started late. I started at 10:50, right?
Yes.
So can I get an extra 15? 15 is enough for me.
So we can give you 15 and at 10:30, 11:30.
Yeah, that is fine. Thank you.
So
Okay, so and we are just about to transition now into the halfway point of the slides, the limits of your laptop. Okay, so your laptop is very powerful. You've used it to watch series, you've used it to shoot emails, you've used it to calculate stuff, but there's a limit to which it can get. There's a limit to the types of problems it can manipulate. Okay, and for those of you who have seen your laptop hanging, it is because of one or more of these reasons. Okay, so one is that just the amount of data in the problems. Okay, if you have a spreadsheet that is 1,000,000 rows, some computers can fail to manipulate all this data. Okay, and therefore will hang. Okay, atomic systems, right? These systems that we want to use to understand drugs, we want to use to understand computation, also are limited. Classical computers are also limited in studying these problems. Okay, figuring out if you work for Amazon, which good should move where in an optimum manner. These are called optimization of problems. They scale as the number of customers grows. Okay, and one of the reasons one of the reasons all these startups are struggling with this problem of delivery, Uber Eats, etc., is because of this. As the number of your customers grows, the need to efficiently deliver goods and services to them also grows, and the complexity of this problem grows. And step in quantum computing. So what we are going to try to do is combine quantum mechanics and computing and create this thing called a quantum computer and try to understand what it is doing. One, I'd like you to notice that look at this sphere and notice something. 0 is up, 1 is down. Okay? Now, typically, your classical computer has these things as separate. It separates 0 and 1 and then builds bricks and houses using logic gates out of that. But a quantum computer surrenders this notion. It says 0 and 1 because I am using waves. 0 and 1 really are the same thing. Okay, and what I am going to do is to try combine 0 and 1 in various ways. So if an object has a lot of 0, it is up here. If it has a lot of 1, it is down here. But mostly the object of computation in a quantum computer is somewhere within the latitudes of this sphere. Okay, and therefore it is a combination of both 0 and 1. And this is a deep thing about quantum information. We call these things bits, okay, 0 or 1. We call this thing a qubit. A qubit is various combinations of 0 and 1. When you carry out a measurement, it snaps. So for example, if this qubit was nearer to 0 than nearer to 1, we would say it is 90% 0, it is 10% 1. Such that if you carry out 100 measurements, 90 of them will snap up as 0 and 10 will snap up as 1. Okay, so it is a very interesting way of representing information. Now, again, you have bricks, but you need ways of combining those bricks, just like we did here, into information. Okay, and how you combine bricks into information in qubits is by quantum gates. Instead of logical gates, you have quantum gates. The important thing, I don't want to focus on the detail here. The important thing is that you need special types of quantum gates, okay? And physicists, engineers, quantum computing engineers, scientists, one of their primary roles is to figure out how to create these quantum gates. You have a NOT gate, okay? But you also have interesting gates that allow you to mix probabilities, to take one state and mix it into up and down, that is, create this sphere. I would like you to look at the extreme end of things like diodes, like speedometers of this picture. That is now a measurement operation. As I said, you can't look at computation, quantum computation, as it is going on. You have to set the circuit, leave it to do the problems, and then measure the result after the computation. So this is a very serious problem. And one of the reasons quantum computing engineers are getting several $100,000 per year, several $1 million per year, is to figure out how to do this engineering problem efficiently. Now, we had spoken about entanglement, and this is where this weirdness of this bit, okay, that is both a combination of 0 and 1 comes together. And this is called entanglement. So what you think about is to think about multiple properties of the system existing in the system at once. It is both up and it is both down, okay? And in this very complicated system, there is somewhere where your answer is encoded. Somewhere in these waves, your answer is there. So you need to figure out ways of suppressing all other parts of the system so that you have only one spike, okay? You have only one spike at the answer is 0 or the answer is 1, okay? And this is the problem of figuring out quantum algorithms, okay? So it is not exactly parallelism. It is not me creating a data center which has 20, the equivalent processing of 100,000 laptops and just throwing the problem at it. It is figuring out how to use this very weird wave mechanics to switch off and switch on potential solutions. So let's say you are doing 1 + 1 is, so there's a place in the wave where the answer is 3. There's a place in the wave where the answer is 4. There's a place in the wave where the answer is 2. So you need to switch off the part where the answer is 3 and 4 so that you get 2. And the formulation of quantum algorithms is essentially how to do this. I'd like you to note this down. I'm not going to discuss them in particular detail, but they are very famous algorithms, okay? And I'd also like you to note that there are not 100 algorithms in my slide. There are like 4, okay? Maybe at most demonstrable, powerful quantum algorithms are probably 10. Algorithms are just how you chain together pieces of logic to solve a problem. So an algorithm is nothing fancy. How you chain pieces of logic together to solve a problem. So one is Shor's algorithm, developed by Peter Shor, a physicist. This does prime number factorization very efficiently, and we will discuss the implications of this for security. Grover's algorithm, this does the sorting of an unordered list or finding an element in an unordered list very, very fast. So you can think about, for example, your laptop. You're trying to look for something in your laptop. You can think about the internet, right? It's an unordered list, unstructured list. And people build algorithms to try find things quickly, try find information quickly. Google is $1 trillion company because they figured this out better than anyone else, faster than anyone else, okay? So Grover's algorithm helps these types of such problems. And then there's phase estimation. Basically, it is important for very many quantum simulations and quantum optimizations. And then there's finally quantum simulation, where you try to model the molecule using a quantum computer. In these 4 cases, we have demonstrated something called quantum supremacy or quantum advantage. Basically, that a quantum computer can do what even a classical supercomputer cannot theoretically do longer than the age of the universe or longer than human beings have been alive. So it can get something done in a month that would take a classical computer 1 billion years. Now, quickly to applications. One is cryptography and security. You see these first 2 algorithms, they are deadly. They are going to break our current cybersecurity systems almost completely, okay? When one builds a sufficiently powerful quantum computer, and the estimate of this is 2030 to 2035, our current security systems are all going to break, okay? So Shor's algorithm threatens something called RSA. You can ask me the details in the questions. I don't want to get into the details. And all these systems are going to be vulnerable in just 5 to 10 years. So we need to think about forms of post-quantum cryptography. We have spoken about this, the simulation of chemistry and metamaterials research, okay? So you want to use quantum mechanics to simulate quantum mechanical systems, okay? So for example, energy storage. Shannon has spoken about drug discovery and optimization of simulations in this particular regard. Logistics, we have also spoken about this. There's something called quantum approximate optimization algorithms, which are used to find efficient routes to distances, okay? So you have a lorry that is supposed to deliver 5 different objects in 5 different locations in Nairobi, okay? How do you figure out a fuel efficient way of delivering these objects as quickly as possible so that the customer does not complain? This is an optimization problem. And here, people use mixtures of classical computers and quantum computers to show this advantage. Machine learning and artificial intelligence. This is a particular passion area for me. You need to find a way of, so machine learning works by taking an object or an idea or a piece of data and just translating it into mathematics and letting the computer understand the patterns of this mathematics, and hopefully the patterns of this mathematics will correspond to the patterns of the data, okay? This is basically machine learning. Translate something into math, understand the math, you have therefore understood the data. And this is why machine learning is also an example of computation. Now, you can figure out ways of taking this data and putting it in the sphere of quantum bits. And then you can teach quantum circuits to learn these bits. And this essentially is quantum machine learning. As far as I'm aware, there are very constrained examples where quantum machine learning systems become better than classical machine learning systems. But it is an area of research, and you can ask me, this is my specific specialty. Now, scientific discovery, it is helpful here. Quantum computing could be useful, obviously, for science, and we've spoken about drug discovery and materials discovery. I want to go quickly to why Kenya should care, and I'll ask for an extra 2 minutes to talk about this. One, Kenya is one of the most technologically advanced countries in the global south and definitely in the continent. Last year, we received the most amount of financial investment in the continent in AI and startups, general startups, okay? So there's a recognition that Kenya is a few years ahead of other continental countries and is a competitor in the global south, okay? So one of the places where one could think of setting up quantum technologies just objectively is Kenya, one of the potential centers of the world. But the current potential centers of the world are actually China, the United States, and the European Union, okay? So what do we do? Very quickly, the opportunities for Kenya is one, we just can build a talented core, okay? When you're training someone to learning quantum computing, they need to learn physics, they need to learn computation, they need to learn the intersection of physics and computation. So automatically they become a very, very versatile individual just by merely the fact of what they know about the world, okay? Second, we could develop cybersecurity expertise, which would be donated in the region, but also used internally here in Nairobi, in Nakuru, in Kakamega, etc. We could build systems of secure storage and transmission of information, and we could learn how to do this, and this would help us transition into our most famous goal, transitioning into a service economy, okay? And then we could think about regional, right? Talk to the South Africans, talk to the Nigerians, the Ugandans, the Rwandans, the Tanzanians, talk about regional coordination of quantum cybersecurity, but also quantum computational research and development. And this will definitely help our startups in the downstream. These are the sectors that you need to be paying attention to, and you can ask me about the details later on. One, banking and mobile money. Of course, Kenya is famous globally for this. Two, telecoms, right? The combination of telecoms and banking is why Kenya has a foot at the technological door, but the door will close very fast if we keep on celebrating M-Pesa for 20 years. So we need to come up with other ideas. Health, agriculture, and energy, transport and logistics, which is underappreciated in the continent and in the country, and government data, okay? So clearly there's a role for government data. We are doing rapid digitization, right? The last time I was signing for my lost ID, I didn't sign in a piece of paper. So we need to think about how secure this information is. The risks are exactly the opposite of the threats, the opportunities. We were attacked by some faction of the Sudanese civil war because of speaking carelessly about the civil war in Sudan, and our banking processes were harmed for at least a day or two. And this is just classical attacks. What would quantum attacks look like in the 5 to 10 years that are coming, right? And we think about that. We also need to think about harvest now, decrypt later risks, okay? Somebody could just store our data, and since it is classical encrypted, could decrypt it once they get that computer that they are looking for, that quantum computer. So we need to fix our problems now. We need to think about post-quantum cryptography now. And a very rough roadmap, and we are trying to craft this as part of a policy framework, a combination of Quantum Kenya and Action Lab and Songhai and Haki. We are trying to fix a roadmap for achieving quantum security. We don't want to build a quantum computer, it's very expensive, but what kinds of partnerships and ecosystems can we structure so that we are able to take advantage of these technologies. So of course, building talent and awareness. We need to think about cryptography very hard in the next 2 years. We also think about funding research groups, right? In the University of Nairobi, in the Quantum and Nuclear Research Group in Strathmore, to do more research on what our country and our region specifically needs. I've rushed through the final slides. Thank you very much. And I appreciate you having me here. I will take questions, and I request that they be easy questions. Asante.
Oh, thank you so much for that. First of all, you're such a good teacher. It was very easy to understand, even for people who do not have such a background. And I hope that with that information, maybe it might not take me to do a PhD in quantum, but maybe I'll understand the Big Bang Theory when I rewatch it, a bit of the academic side. So in the meantime, I think we could take questions. Let me restrict the time and request that you give us 10 more minutes of your time, so we finish at 11:46 or at least 11:50, so that we give you sufficient time to ask questions. Feel free to ask questions in the chat, or if you're in a space, you could unmute yourself and ask the question. So as people are thinking about their questions, I think you made me think about high school and physics and how, we thought it's not very useful information. And I think that was cool. You made me think, no education is useless. So someone is typing their question. I hope you can see that in a few. And maybe I could ask, because we called this demystifying quantum. Why do you think, on a very social, economic level, even at that, why do you think it's a mystery? Why are we demystifying it?
And this relates to your earlier comment. Thank you very much. That is a very good question. I think there is a problem with science education in the country. Why is it useful? With due respect to the framers of the physics curriculum, why is it very useful to spend 2 years talking about how doors lock or how doors swing? So levers and all these turning points. By the time you get to Form 2 or your second year of high school, you're basically bored with physics. It's hard and boring. It's not hard and rewarding. So we need to find ways of restructuring physics education and science education in the country, where we accept there's some level of difficulty. There's some level of difficulty in history and art, but people tend to process history and art quite a little bit easier than this stuff. So we need to ask ourselves, what are the humanities people doing in digesting the difficulty of their subject in a manner that is interesting, and try to do similar things. And also introduce atomic physics in Form 2. Trust young minds. Young minds are quickly developing. You need to just trust them and say, okay, you can absorb some of these ideas. Once a teenager is exposed to these ideas, they become interested in developing them. Okay, and this is why in the United States, in Europe, right, you have PhD students that are 20 years old, 21 years old, okay? They're in their 20s because they've been studying forms of atomic physics and quantum mechanics for 10 years, okay? So we need to figure out how to make the curriculum exciting. Now, there's a certain inherent difficulty that needs to also be broken through. The student, the person who wants to learn these things actually needs to discipline themselves and sit down and study. Yeah.
Okay, thank you. I can see Kennedy has a question, and then we'll take Kennedy and then Nomalanga. Please go ahead and unmute yourself, Kennedy.
Hello, Lynette. Hello, Carrington. Hear me?
Yeah, we can.
Thank you, Carrington, for that very wonderful presentation. It sure was very enlightening and very without diluting the content. I think you are part of the solution to that science education that you're talking about. So maybe my question is around in terms of the understanding. Of course, what you've done, you've given us a very brief overview around the area. So, do you think it is possible for someone to be able to go deep into that particular field, into that particular field, without that solid mathematical and physics background to understand the physical system, and if so, what are the areas, or that you'd say the minimum for going in that particular for going to that particular direction? So some sort of a prerequisite, as you know, for understanding that. Thank you.
Thank you very much. That is a very good question, Kennedy. So the problem with interdisciplinary fields is that they require some level of depth in multiple fields, okay? So if you want to, for example, understand quantum computing, you need to take your time and understand some physics, but also some computing, and then how these two interact and what are the fundamental primitives that will allow you to connect the two, okay? But in terms of like practically, it really depends with what you want to do, okay? So there are some people who are in quantum policy, okay? You need some level of understanding of the field, just like in data management and data policy. You do not need to figure out how data is represented in semiconducting circuits and flip-flop gates, etc. But you need to understand the general abstraction above that level that can allow you to speak competently about governance mechanisms for data. Okay, so the Data Protection Agency in Kenya, or the Data Protection, I've forgotten their name, Office of the Data Protection, blah, 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 does not have data engineers only. It has multiple people with multiple backgrounds with some competency, okay? If you want to be a quantum engineer, a good place to start is a book called Jack Hidari, Introduction to Quantum Computing or something. Yeah, Jack Hidari is the author. So this book is organized very interestingly. The last 5 chapters are basic introductions to mathematics, so that the person who knows does not need to like look at the math, but the person who needs to starts with those chapters, and then now you can build up the concepts in your head as you're going along. So sadly, since Galileo, mathematics is the language of the universe, blah, 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 there's some level of mathematics that you need to be a quantum computing engineer or a quantum computing research scientist. But I would like you to understand that this is not the only role in the industry. You can be an educator, you can be a quantum AI policy person, you can do multiple things. And in fact, you should build up the capacity to do multiple things within the industry. Cybersecurity, for example, is one interesting aspect that does not need you to be deep in the physics of particles and atoms and molecules. Yeah.
Thank you, Carrington. I'm very encouraged that we have experts from our country with that kind of expertise. I think we can have further discussions offline. It's a very fascinating field. I even see we have Shannon, Claude Shannon. So that's a good sign. Yeah. So thank you for that for your feedback and for the presentation as well.
Oh, thank you. Thank you, Namalanga, for that comment. I can see some questions have come in we have real-time text because your questions will also go into the recording. But someone is asking, and I think I'll combine because the point here is about practicality. So there are people who learn by doing, and of course, you've shared the book by, I think, Jackie Derry. They're asking what are the available quantum computing systems that they can use remotely. And then someone is asking, they've done physics and they're currently doing an MSc in data science. How can they blend the two to do research that impacts Kenya, possibly the world also, because we're trying to get ahead, right? So yeah, maybe you could help us with that for the practicality, and then and I can see a lot of people we have are around computer science, physics, data science, engineering. How can we, you said it's multidisciplinary, how can we just leverage on all the skills that we already have?
Thank you. Thank you to the people who have asked that question. And yes, we want that our research and technology has impact beyond the borders of Kenya, right? Yes, African solutions to African problems is a wonderful slogan, but China has China's solutions to the world's problems. And that is the trick, okay? That is the trick. If you want to get wealthy, solve problems that other people other than your country are interested in. Okay, now, in terms of just the practical curriculum, it is again very student, very person specific. If you have a background in physics, and it is one of those sad situations of our system of learning that subjects and fields that actually come out of each other are normally separated. There's a practical reason for this. If I am a student and I'm doing physics, I don't need 40 units in computer science and 30 units in philosophy. But you see, all of this stuff is somehow related. And we need to figure out ways, like practically for universities, to make sure that the physics student is getting not just computational physics courses, but computer science courses, and vice versa. The computer science student is also getting physics courses. After all, computation is a physical problem. So if you're coming from the computer science field, I would say practically you need a few months of math, and you can just like ask ChatGPT nowadays. It is very good with suggesting things. Give it your information, and then it will tell you, you need this particular math, you need this particular math, go and study it. And then the physics on top of the math. And then now you have the required muscle to play around with quantum computing. But there's also the reverse. As I've said, for my physics courses, I was only taught how to use programs, how to code for certain pieces of data, how to code for certain pieces of simulation. I wasn't taught computation, okay? So I myself needed to take courses and read books on computation. So everyone has a different puzzle that they need to fill in to figure out their path. Yeah. And interesting things that you can do here are, of course, quantum machine learning. I think quantum machine learning is software heavy rather than hardware heavy. And therefore, it allows you to think about problems and make progress in a manner that you don't need really a quantum computer, but at some point you're going to do. There are practical courses that you can take. For example, from IBM. IBM can actually give you limited access to a weak version of a quantum computer so that you can actually learn how to program a quantum computer, to give it tasks and get input from it. So please go and check the IBM course and how to apply for IBM compute credits, quantum compute credits. I think institutions can also email IBM if they're interested in getting some compute hours from them.
And now I think we'll address also, we are coming to the machine learning. Though I think I should extend the machine learning by asking a question, then I'll follow up with the cybersecurity. Dennis is asking machine learning algorithms and the quantum algorithms, QML, are they similar in terms of how they work? And then now, after you answer the machine learning people, the cybersecurity people are here and connected to that very closely. And I know there is an advocate listening in. Cybersecurity is concerned. Are we adequately prepared for, the harvest now, attack later? And someone is asking is what extra resources or skills do they need to in terms of cybersecurity now that they're interested in quantum security? So maybe you could start with the ML and then go to the cybersecurity and protection, data protection.
Thank you. So I'll start with machine learning. And as I said, machine learning is how do you transfer data into mathematics and learn patterns of the mathematics of data, and then use that to make inference about the behavior of the system that generated that data set. In technical detail, machine learning projects data into high dimensional spaces and then carries out inference in these high dimensional spaces and then projects them down to lower dimensional spaces. For example, ChatGPT works in 50 or 60,000 dimensions, okay? Now, this particular technical point that machine learning is about this upward projection into high dimensional spaces is important for quantum mechanics because you remember the sphere I showed you. That sphere of 0 and 1 actually lives technically, and I need you to believe me. So this is a sinimimi na kusho moment. It lives in something called a Hilbert space. And this Hilbert space is very high dimensional. And in fact, in some versions of quantum mechanics, it is infinitely dimensional, okay? So the exact thing that machine learning engineers are learning to do, take these things, put them in very high dimensions, learn about them in very high dimensions, and then put them now to low dimensions, is the very thing physicists have been learning to do with the nuclei, right? Nuclear physics, atomic physics for at least a century, okay? And therefore, quantum machine learning is about what are efficient ways we can take data, put it in an infinite dimensional quantum mechanical space, do our stuff there, and then push it down to low dimensional spaces, okay? And this is the problem of quantum mechanics, quantum machine learning. Now, as to the question of whether these algorithms are exactly the same, the answer is yes and no. Why? There are multiple classical machine learning algorithms and there are multiple quantum machine learning algorithms. Now, in the simpler versions of this problem, 2017, 2018 researchers in China and the United States used to think about, we have something called, and forgive me for the jargon, a support vector machine, a linear regression. Can we build analogs of these classical machine learning algorithms for quantum computing? And they found actually that it is in general true that you can do this. There is something called, and I'm sorry again for the jargon, a reproducing kernel Hilbert space that allows you to project the two to each other, okay? You can map one problem to another. Now, it has also been demonstrated that if you build particular forms of quantum neural networks, you can find that they are universal approximators, okay? So universal approximation is this idea that I can use a neural network to understand any form of any data, including text. And that's why we've built AI models that process text, okay? Now, do we have the same thing for quantum neural networks? And the answer is yes. So there's some similarity and there's some difference, and huge differences actually, that then project into advantages for quantum machine learning. Now, to the cybersecurity. Are we secure? No, not even against Sudanese rebels. So we are not secure. We are not even secure against classical attacks. For those of you who are keeping up with AI research, there's an AI agent that OpenAI has not yet released that was being evaluated on a test. So it figured out how to break away from its sandboxed environment. There's usually a secure environment that has no internet access. So it figured a way of breaking out of that and breaking it into a cloud service provider for AI called Hugging Face. So it broke into, ikaiba mwa Kenya huko, ikarudi ikafanya exam na ikapita. So we are not even secure against our systems right now have 0-day exploits that allow us to basically, and this is one of the most secure AI research companies in the world. It's not SHA. It's one of the best secure AI companies in the world. So we are not even secure right now against AI 0-day exploits. So we are not definitely secure against quantum attacks. Now, what do? First, for the next 2 years, we just need to build capacity. We need to figure out a way of introducing post-quantum, write this down, PQC, post-quantum cryptography courses in Kenya, right? And what kinds of systems other people, for example, the National Institute of Standards and Technology in the United States is thinking about. For example, right now, I think latest iPhones are being released with some form of post-quantum cryptography. And we need to understand and we need to deploy. It does not need quantum technology actually to deploy. It can be abstracted away into some software update for a certain company. And if you can start a startup doing this particular thing, I wish you the best and make your money.
Well, that was very, very well answered, as Dennis said, and excellently done. Thank you so much for the conversation that we've had. I think we've all learned a lot. We have, Kwanzaa, I don't know why you are apologizing about the jargon. I can't wait to use the Schrodinger's equation on someone. And we have learned about algorithms. And what you've done really is you've triggered various applications. And especially, I know there are many people from different backgrounds to whom this information may be helpful in their different capacities. And that spark is what will lead to more research, more conversation, more information, and also better protection in the future. Thank you also for those who've asked their questions. For those when you're wameshikilia ndani, I hope they've been asked on your behalf. Feel free to also reach out to us. I think my email is on the poster that was shared. I'll be very grateful not to answer and pass it on to an expert in the field. But thank you so much. Thank you for also allowing us to extend your time and being gracious enough for that. And we hope this has been of great value to you. So go out there and explore quantum computing. Thank you so much, and see you later. I'll send. We'll edit the recording and then send it out. Sawa sawa. Bye, guys.